Hello, we present our research, H2O-SDF, two-phase learning for 3D indoor reconstruction using object surface fields. Given post-multiview images of an indoor scene, our research aims to reconstruct detailed 3D geometry in two phases, holistic surface learning for overall geometry and object surface learning for object details, guided by a novel concept, the object surface field. Recently, many studies have shown that 3D surface reconstruction can be effectively achieved through neural implicit representation. While these works perform well in reconstructing objects, they struggle with indoor scenes, which are a mixture of room layout with low-frequency, large-scale surfaces and various objects with high-frequency, small-scale surfaces. Therefore, recent research on indoor scene 3D reconstruction utilizes geometric priors such as semantic segmentation, normals, or depths, which are extracted through pre-trained networks or multiview stereo techniques. Despite using priors, limitations persist in intricate areas like thin structures. The graph indicates that higher SDF values lead to a quickly vanishing loss gradient, making it difficult to reconstruct thin objects. Thus, due to the vanishing gradient issue, complex object surfaces are harder to reconstruct than smooth room layouts. To address these challenges, we propose a two-phase learning approach composed of holistic surface learning and object surface learning. Our first phase, holistic surface learning, addresses the inherent conflict between color and normal information. This conflict results in a discontinuous representation in textureless regions and an over-smoothing representation in regions with fine details when color and normal information are applied uniformly. To mitigate this issue, we introduce a technique to reweight normal and color loss using normal uncertainty, which exhibits low uncertainty in planar regions and high uncertainty in texture-rich surfaces. Building upon the overall geometry from Phase 1, our Phase 2 object surface learning focuses on the objects to capture more detailed high-frequency geometry. The core driver of object surface learning is a novel concept, the object surface field, or OSF for short. Object surface learning includes a 2D object surface loss that learns the initial form of the object surface fields and a 3D object surface loss that learns the detailed form of the object. Similar to color and normal loss, the initial form of OSF is learned by minimizing the difference between the predicted OSF of the ray and the given 2D object mask. These 2D object masks are obtained from a pre-trained segmentation model. Although the 2D object surface loss can build the initial form of the OSF, the information provided by 2D object mask is insufficient to create accurate 3D geometry. So we propose a 3D object surface loss for learning of precise 3D object geometry and supervising the object surface area. The 3D object surface loss is designed for both rays that intersect objects and those that do not. It increases the object surface probability when a ray enters the zero-level set of the SDF and decreases it upon exit. For rays intersecting only with room layout surfaces, the object surface field should maintain a low probability. We mathematically explain how the OSF learns the surface of the object and how a well-learned OSF enables the SDF to capture detailed geometry. The 3D OSF loss helps deliver gradients to small objects, mitigating the gradient vanishing issue. Additionally, we propose a refinement loss that enhances the OSF using points extracted from multiview stereo and an OSF-guided sampling strategy that samples points according to the object surface probability. The qualitative results on ScanNet datasets show that our methods outperform on both smooth room layout and fine details of objects. Thank you for watching our video. Please visit our project page and refer to our paper for more research and analysis.